Welcome back, Math 30-2. So we're going to continue on our video lessons here of set theory. So this year you can see that we're going to start on the next page, talk about applying set theory notation, and then we're going to continue on with the number system and talk about more Venn diagrams and how to solve more complex Venn diagrams, such as the 2-circle and a 3-circle Venn diagram, where you're given limited information. We already started that with one in the previous video, but we're going to add a little bit more complexity by adding an extra circle. But before we start that, let's look at this set that we have here. So let's see if we can fill these in. Let me just get the pen working today. There we go. Yeah. So just remember that the big rectangle in this Venn diagram usually represents the universal set. So let me just write that in here. Universal set. Denoted by the U, capital U. That's all the numbers that we have, all the natural numbers between 1 to 40. So if you remember the natural numbers are numbers 1, 2, 3. They're all the numbers with no decimals. And they'll include 40 and 1 because of this word inclusive. Right? So the word inclusive means that you're going to include those two pieces as well, the last pieces. Multiples of 8, if you remember how to calculate multiples, multiples of 8 would be any number times 8. So 8 times 1, 8 times 2, 8 times 3, etc., etc. So I can write all those down. So 8 is a multiple of 8. That's just 8 times 1. 8 times 2 is 16. Oh, sorry, I'm having problems with hitting the wrong button here. 16, that's a 16. 24, 32, and 40. So those are the multiples of 8. The multiples of 4 are 4, 8, 12, 16, 20, 24, 28. I'm running out of space here. I'm just going to write down on the bottom here. 28. So what else do you have? 32, 36, and 40. So those are all the multiples of 4. And the multiples of 17 are 17, 34. And the next one after that is 51, which is beyond our universal set. It goes up to 40 and nothing more. Okay, so now once we know what these sets look like, I want to figure out how do they fit in this diagram that we have here. Are any of these sets disjointed? So remember, is there any sets that don't have any overlap? Are there sets that are completely within others? So are they subsets of others? All of these sets, E, F, and S, they're all subsets of the universal set. They all belong within that set. You can see that they're totally encapsulated. All of the numbers that we have here are inside the universal set. There are other numbers beyond, like it doesn't just stop at 40. It can go to 44, 48, et cetera, et cetera. Those numbers possibly could be in those sets if you think about that. But let's just say that these sets stop at 40, and same thing with this set down here. So these sets are completely encapsulated in those. So they are subsets. Now let's look at this one down here. So the multiples of 17. Multiples of 17 are 17 and 34. If I look at my other sets here, neither one of these sets have a 17 or 34 in it. So that set of 17 is this circle here because it's disjointed. It doesn't have any numbers in common with the other sets. Now, the other two circles here, you can see one circle is completely inside the other. So if I look at these two sets here, I could see that all the numbers that are in E are inside of F somewhere. There's an 8 here, there's a 16, there's a 24, there's a 32, and there's a 40. So all those numbers are in there. So E is this one here. It's completely inside another set. So I'll call that E. If you want to put the numbers in, you can. Actually, I'll just put a big E there, put a big S here. All right? Just erase that other E. Okay. Now, F is the one that has E in it. There's E there, but it also has additional pieces. So I could say F is this larger piece here. I have a problem when I overlap my highlighting here. It gets a little bit dark. But that piece there, that is F. Now there's a bunch of other numbers that are outside of these boxes, like the number 1, the number 2, the number 3. So there's some numbers out here. There's a bunch of numbers here that don't belong in these other sets. So they're still within the universal set. So they're still there, but they're not in any of these little circles that we drew. There might be in other circles if we make other circles to go with them. We already answered this question down here. Are any of these sets disjointed? Yeah. There is no intersection between S and F and S and E. So these sets are disjointed. Okay. Now, you can denote that by using, we'll do that down here, create 3 statements that will make the set notation above, using set notation that are true. So using F, S, and S. So if I said that S intersect with F, I'm looking here, where does S and F intersect with each other? Well, they don't. So that is an empty set. So that's my set notation. There's no intersection between the two. But I do know that if I said this statement, E, where does E and F intersect with each other? Well, they completely intersect with E. Right? F and E have all of E in common. So everything's there. So this also just says that E is a subset of F. E is completely within F. So that's a true statement there. I'll just use a highlighter to do this one. All right, so that's a true statement. But it's not said, you can't say the other way unless they are exactly the same set. Like if E and F are the same, then I could say this, but I can't say F is a subset of E because there's numbers in F that are not in E, right? Yeah, there's numbers in F that are not in E. So you can see here, there's numbers in F like 12, 28, what else? 36. Those numbers that don't belong in E. So F is not in the subset of E. So that's a false statement. S is a subset of the universal set. All these sets are the set of the universal set. That is true. The complement of F, okay, so F are the multiples of 4. So what is, remember this little symbol stands for not. What is not a multiple of 4? So a multiple of 4 would be like 1. Okay, that's an odd number. 2 is not a multiple of 4. But that's an even number. What other ones? Like 3, 4 would not be there. 5, 6, 7, 8, 9, 10. Okay, so this is some of the examples, some of the numbers. It keeps on going. You notice I didn't have 4 in there. Like there's a 4 missing here. There's an 8 missing here. Because those are multiples of 4, and we're looking for what's not the multiples of 4. So we also look at these numbers. It's 1, 3, 7, 9. Those are odd numbers. Okay, so far so true. But there's a 2 here. There's a 6. There's a 10. I'm going to say, are them not the multiples of 4s? Are they all odd? No, they're not all odd. That's a false statement. There's some even numbers inside that. In this example, is the set of natural numbers from 41 to 50. Is that considered an empty set? Yeah, in this example, because the universal set was 1 to 40, so 41 and on don't exist in this example. So I would say that's an empty set. It's technically not if you consider the universal set to be all the natural numbers, but they give us limitations here, from 1 to 40. So 41 to 50 are beyond the set. So I would say that's an empty set. So we have a few other things here. So we could say, so we already said here for the true statements we want to create. So like we have some statements up here are true or false. So if I want to create another true statement using set notation, like the intersection between S and F, that's an empty set because they're disjointed. The lame way would be saying S and E are also an empty set, like the intersection between the two. You could say that the intersection between E and F is just E, because that's what they have in common, everything that's in the multiples of 8. I can also say the union of E and F is just F. It's all the numbers of F, because that's what because E is complete with an F, so I can say that as well. Because I have a circle, I have another circle, And remember, the union is both of these circles, everything that's inside these circles. So you notice that I just colored in that top circle, which overwrote the E that we had there. So this is E here, this F out here. Okay. The reason this other one's true is if I have two circles, and I look at what they have in common. So here we highlight the middle part here, and then I can go out here and I can highlight here. Oh, you can see that little green, that area turned green there. So that's what they have in common. So in the intersection, that part there, what they have in common is my answer, and that what they have in common is E in this situation. It's E and F. Okay. Okay. A couple other things that we want to worry about is like, first of all, let's just review what are the number systems. Like we talked about what is a natural number. So a natural number, denoted by the capital letter capital N, includes all the numbers from 1, 2, 3, and on, right? So these are numbers without decimals, right? They don't include 0 and they don't include negative numbers. All the positive numbers from 1 up, right? A whole number, denoted by the letter W, is the same as a natural number, but includes a 0 this time. So that's the new piece here. Okay, so I'm just going to highlight that. So this has a 0 as well. Right? Integers, denoted by the letter I, are pretty much the same as whole numbers. So they have 0, 1, 2, 3, 4, all the way up forever. But they also have negatives, 1, negative 2, negative 3. Backwards, you keep on going backwards. If you want to put dot, 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 there you can. So the new pieces here are negative numbers. But you know right now that they have no decimals so far. Right? Now, a rational number is denoted by the letter Q. The reason we don't use an R for rational numbers is because the letter for real is I call it a double bar R, but you can just write a regular R if you want to. That's the letter for real. So they need another letter for rational, so they pick the letter Q. Now, a rational number is any number that can be expressed as a fraction. That's hard to write out all those numbers here, so I'm just going to say any number that can be expressed as a fraction. Right? So that doesn't include numbers like pi or root 2 and stuff. Now, an irrational number is any number that cannot be expressed as a fraction, not a fraction. Now, how do we know if it's a fraction or not? Well, it could be a fraction if it repeats, like if the decimal repeats, or it terminates. Either one of those two things. It doesn't have, if it terminates, it's obviously not repeating, but it's got to repeat. And it could repeat any weird numbers as long as it repeats over. It could repeat 1, 2, 3, 4, and then 1, 2, 3, 4. It could repeat like a million digits and then repeat those million digits over again. Right? So that would be a fraction. Or if it just stops like 3.5, that's also going to be expressed as a fraction. Not a fraction is that if it doesn't repeat, non-repeating, non-terminating. Okay, so like pi and stuff, they just keep going forever. Now, real numbers is everything. Everything we deal with here, like all the above. I'm going to say that, all the above. We do have things called imaginary numbers and complex numbers. That's beyond this course, is beyond high school pretty much. So if you ever go to a university course, they might talk about imaginary numbers. Maybe not. They're not very useful unless you do like higher level engineering or some calculus stuff. So not everyone's going to use them. They're not very useful in everyday life. So what else do we have here? So this is our Venn diagram here that we have. So the real number system would be considered our, let's say, our universal set. So all the numbers that we deal with are in the real number system. We have the rational numbers, we have the irrational numbers, and then you notice that they're not in the same circle. There's like you'd almost draw like a circle around rational numbers here, and draw a circle around irrational numbers. And you notice that these two circles they don't intersect each other. They're disjointed. There's no numbers that overlap between the two. So if it's considered rational, it's not irrational. If it's irrational, it's not rational. So my irrational numbers like root 2, pi, some other numbers like phi, the square root of 3, just numbers that are not very nice. Rational numbers would be like 1/2, 2/3, 5/10, or I guess 5/12 or something. Just pick some of the random numbers. These are all fractions. But rational numbers also include everything else. They're nested within each other. You can see that. You can say integers are a subset of rational numbers. Right? Whole numbers are a subset of integers. Naturals are a subset of whole numbers, integers, and rationals. Right? So if I put a number in here, let's say I put a number in the real or the natural numbers here. So got this here again. Like the number 1. That's a natural number. 1 is a natural number. It's a whole number. It's an integer. It's a rational number. And it's a real number all at the same time because they're all nested in there. If I kind of just get rid of this circle, that 1's going to fit in the whole numbers. If I get rid of the whole number circle, now it's in the integer. If I get rid of the whole number or integer circle, now it's in the rational. If I get rid of the rational circle, now it's in the real number system. So 1 is in all of these systems, but like 0 would be here because it's not a natural number. So I can't say 0 is a natural number, but 0 is a whole number, an integer, a rational number, and a real number. -3 is only an integer, a rational number, and a real number. Here we have some examples here. We got like half. Half is not an integer, but it is a rational number and a real number at the same time. So that's what we're going to do down here. We're going to classify some of these numbers. So if you want to, you can try to pause the video and try to think about which sets does the number 53 belong to? 0, -7/9. It's a multiple choice question, but you can think about all the different sets that these could be in. I could throw in a different one over here, like pi. Which sets does that belong to as well? Okay. All right. So hopefully he paused and tried it. So 53, because what we're trying to identify, we want to know which one is it simultaneously a rational number, integer, a whole number, and a natural number at the same time. Okay. So let's do 53. So 53 is a natural number. Actually, I don't have to put the little curly brackets there. It's a natural number because it's not 0 and has no decimal. It's a whole number because it is a natural number. It is an integer because it is a whole number. It is a rational number because it is an integer, and is also a real number all at the same time. Because it was a natural number to start off with, as you follow out the system, out these little nested little system, use everything else above them as well. 0, like we talked about here, is not a natural number, but is a whole number. Because it's a whole number, it's an integer. Because it's an integer, it's a rational number. Because it's a rational number, it's a real number. -7/9 and 7 1/2. These are two numbers. 7/9 is a repeating decimal. I think it is. Let me just double check. Yeah, 7 repeating. It's negative. So you can actually write that out. And 7 1/2 is 7.5. Okay, so that's a terminating decimal. This is a repeating decimal. Both of them are fractions. You can see they start off as fractions. So there's no doubt about that. And because they're fractions, they're not a natural, they're not a whole, they're not an integer, but they're a rational number. They're both rational numbers. And since they're rational, they're real. So there are only two sets in this case. Pi is an irrational number, but because it's irrational, it's also real as well. But it's neither one of these other ones. So my answer for this one is 53. It's simultaneously a rational number, an integer, a whole, and a natural number at the same time. They're all real numbers, because that's the numbers we talked about. Okay. So I'm going to stop the video at that point there, and then, oh, actually, let me just double check. No, I won't stop the video there right now. We'll stop the video at this Venn diagram that we have at the bottom here. Okay. The 3-circle Venn diagram, we'll just do right now. We'll just talk about from this Venn diagram of the real number system. Identify the complements of real numbers. Remember what the complement stands for? Complement is not. What is not a rational number? So what is not a rational number is everything that's outside the rational number circle. Remember what we did before? You could treat this box to be a circle and this box over here to be a circle. These two boxes don't touch each other. So what's not a rational number is all this irrational stuff. So that would be irrational numbers because they're disjointed. Oh, that just answers this question here. The sets Q and Q not, or sorry, no, technically a not in some computer science stuff, are disjointed. Okay. N is a subset of which sets? So what does N belong? N is the natural number, but N is completely inside the whole numbers. N is also completely inside the integers. N is completely inside rational numbers, and N is completely inside the real number system. So he's inside all of those, right? Because he's nested within them. There's no number that's outside of natural systems that doesn't belong inside a whole number. Okay. So what numbers are whole numbers but not natural? What numbers are whole numbers and not natural? Whole numbers not natural. So go back up here. If I look at this whole number circle here, I'm going to put one number here, 0. Because that's the only number in that circle that's not a natural number. Natural numbers are 1, 2, 3, 4. Those numbers are whole numbers. The only thing different between these two is that 0. So what number is a whole number, but not a natural at the same time? 0. Not an empty set or anything, but 0, the number 0. Okay? So what is the union between not a rational number and not an irrational number? So I got two nots here. Well, what's not a rational number? Well, that's an irrational number. What is not a irrational number? Well, that's a rational number. So what's the union between these two? That's all the numbers still. Those are just exactly the same thing. It's just a weird way of saying it. So we have a couple true statements I can make here. I already wrote a few here, like N is a subset of W. That's a good true statement. You could just write any one of those other 4 things up there as well. I could say, because the two sets are disjointed, that Q, the intersection between Q and Q not here, so rational numbers and irrational numbers, that's an empty set. So there's nothing in there. What's another one I can say about these two? That's a weird one. I could probably write down that an integer is a subset of rational numbers because an integer is completely within that rational number circle. I think that's all I really need to say. I could also say, like, weird ones would be like, this would be the same as saying, if I wanted to do the union of integers and rational numbers, that would just be rational numbers. That's all it is. Those would just mean the same thing. Let's see what oh yeah, so that's where I was going to say we're going to stop. So I'm going to see the next video. We'll continue on. We're going to do some 3-circle Venn diagrams. There's much more, many more problems here. I'll talk about how I expect you guys to try to solve them before I actually do them. But at that point, we'll see you later. Bye.